Are you ready? Yeah, okay. We're going to do 10-1B, which is really 10-1A, part B, and then 10-1B. Never mind. All right, 10-1B. We're going to stick with some probability. I hope the probability that I finish all the notes is 100%. I hope so. Okay, so here we go. We're just going to jump right in. We learned how to find the probability. It's the probability of the outcomes in an event over the probability of, or the number of outcomes in the sample space. And so let's go ahead and try a problem now, okay? And it's about chocolate. So, number 1. All right, it says here that suppose that you open a box of a dozen chocolate-covered chocolates, and it offers 2 of them to your friend, Val. Val likes vanilla creams the best, but all the chocolates look alike, right? The chocolates, they come in that box, they look exactly the same, but they're different. All right, here we go. This is what they say. If 4 of the 12 are vanilla, so let's write that down. 4 are vanilla, okay? That means that 8 of them are going to be chocolate, because there's 12 total. It says here, what is the probability? Now she's going to pick 2. She's a pig, right? She's going to eat one, and she's going to eat another. And we want to find out what is the probability that she's going to pick 2 vanilla, because those are her favorites. It's probably not going to be very good probability, is it? No. Are you okay today? You look super tired. Perk up. Nope. Okay, that didn't work. Telling someone to perk up doesn't work. Okay. All right, so what's the probability that she gets 2 vanilla? So this is what I like to do. I like to find the probability, there's 2 events going on. We're going to multiply them because it's the probability of them together. It's and. This is an and problem. It's a vanilla and a vanilla, okay? So what's the probability that she gets a vanilla? You open the box. Here, take a chocolate. What's the probability? Perfect. 4 out of 12 is that she gets, on this first choice, she gets a vanilla. Now, she has eaten one. Now, what's the probability that, now this is vanilla, okay? What's the probability that she gets another vanilla?
3 out of 11.
So good. You did it. Times 3 out of 11. Because once she picks a vanilla, there's only 3 left. And once she picks a chocolate, there's only 11 left. Really good job. And then you can multiply this, 1/11. That's not very good, is it? What is 1 divided by 11? Someone probably knows that in their head. It's like less than 10% chance that she's going to get 2 vanilla. That's small, huh? It's like 9% chance. Okay. The other way to do this problem, by the way, there is another way. And I don't know if some of you are thinking this, but it could have been something like this. Out of the 4 vanilla, she's going to choose 2 of them. And out of the 12 chocolates in the box, she chooses 2 of them. And these are exactly the same. That's actually another way to look at it. I kind of like this better, you know, because I'm not worried about C and P and whatever. But, yeah, that's another way to look at it. All right. The lottery. Have you ever played the lottery? Don't. It's throwing your money in the street, in the trash. Okay, so let's say that you want to play a lottery, and let's say that they're going to choose, you have to choose 6 numbers from 1 to 49. What's the probability that you're going to win with your 1 ticket? Okay, you have 1 ticket. What's the probability that you're going to win? Well, there's 1 winner. I mean, there could be more than 1 winner because people have the same numbers that they pick. But what you're going to do is the winning number is going to be out of the 49 numbers, they're going to choose 6 of them. So that's the total amount of different possibilities of choosing 6 numbers from 49. And that number is huge. What is it? Whoa. Oh, and what goes up top? You have 1 ticket. Yours is one of those ways, right? So 1 out of the 49 choose 6. You have a 1 in 139,83816. 13, almost 14 million chance of winning. A 1 in 14 million chance of winning. I wonder what my chance was winning for the Hamilton tickets. I don't know. What's the probability that I can win again? We'll find out. Okay, here we go. Next thing is number 3. All right, do you know your blood type?
Yeah.
You do? I don't think I do. It's bad. All right, how many blood types are there? Well, there's a lot if you choose negatives and stuff, but in general, it says here, according to the American Red Cross, blood types in the U.S. population, 45% of the U.S. has a blood type of O. That's the most prevalent, type O. 40% have a blood type of A. Are you A?
No.
11% have a blood type of B. And only 4% are AB. I'm actually AB negative. Yeah, I gave blood once and then they kept calling me. But then I tried to give blood again and I got denied. They rejected my blood. It wasn't good enough for them, they said. Yeah? You did too? Were you anemic?
Well, they were like, you don't have enough iron in you.
Yep.
Like, eat more steak and other things.
Steak and like green leafy greens. Aw, look at that. In the middle of class. Sorry, you didn't win. You can't see that, can you? It says I didn't win the Hamilton tickets for today, which is good because I have to chaperone the dance tomorrow night. Okay, here we go. I would have just bounced on them though, like peace out, gotta go. Now, here we go. What is the probability? So here we go. We are going to choose 2 people at random. Choose 2 people at random. Okay? What is the probability that they both have type O? What's the probability that they both have type O? Yes.
So does that mean we're going to multiply because it's both?
Exactly. Yes. So the probability of O and O means you take your probabilities and you multiply them together. That's exactly right. So the probability of O is 0.45. The probability of O, 0.45. So the probability would be 0.2025. You can write those as decimals. You can write them as percentage, whatever your preference is, okay? You could say 20.25% chance. That would be fine. All right, so that's A. Letter B. Here we go. They're going to get a little trickier. What's the probability that neither one is type A? Neither one is type A. Well, let's do all the other ones, right? If I don't want type A, let's do the probability of not A times the probability of not A. So what's the probability that someone doesn't have type A? What would it be? 60, yeah, 0.6. Okay, so 60% that they do not have A, because what I do is I add up all the other ones, type O, type B, and type AB, and that makes 60%. And so I'm going to take type not A is 0.6 times 0.6, and that's going to give me, what is that, 1.2? No, 0.12? 0.36. I was multiplying 6 times 2. 6 times 6, so that would be 0.36. So 36% chance that neither one is A. All right, letter C. This one's tricky. Are you ready for this? What's the probability that you pick random 2 people and they both have the same blood type? The same blood. Okay. Now this one's tricky because if they have the same blood type, they could either both have O, or both have A, or both have B, or both have AB. Do you get that? Those are all separate things. So you're actually going to take all those probabilities and add them up. So we want to find the probability of OO. That's one way that we can get the same blood. We want to find the probability of AA, the probability of BB, and the probability of ABAB. I know, right? Okay, and so you get them all. So we're going to go 0.45 times 0.45, which we already got, 0.2025. The probability of getting an AA would be 0.4 times 0.4, which is 0.16. Probability of BB is 0.11 times 0.11. Ooh, sorry about that. Which is 0.0121. Ooh, hardly any chance of that happening. And then the last one is 0.04 times 0.04, which is 0.0016. You're going to take all of those probabilities and add them up. Because this is an OR problem. It's an and an OR, isn't it? It's and because it's this and that. That gives me that. But then it's OR because you could either have O or A or B. Okay? And you get 0.3762. There you go. So tricky. Okay, so that's the first part. That was the end of 10-1A. I should have called that letter A, just some probability stuff. And now we're going to move to part B. And part B is going to be a little something called Venn diagrams. Have you heard of Venn diagrams before? I bet you have. They're very helpful. You may not like them, but they're actually very helpful. They were invented by a man named John Venn. He named him after himself. Yeah. 1834 to 1923. He was an English logician. What's a logician? You studied logic?
Yeah.
Yeah. How are you a logician? What's your profession? I'm a logician. What? A magician? That's pretty cool. No, a logician. Oh, really? Okay, I'll see you later. Right? All right. So, Venn diagrams. Now, Venn diagrams, they're used in set theory. They're helpful to visualize the relationships, among other things, in sample spaces. So, here we go. We're going to start. They're really good. They're going to help us. Now, it says here, number, what are we on, 4? Yeah, number 4. Okay. It says, at Pascal High School, that sounds like a pretty cool high school to go to, 54% of the students are girls. 54% are girls. 62% of the students play a sport. Oh, that's pretty good, huh? I wonder what that is here. And half of the girls at the school play sports. Half of the girls play sports.
Could we just put 27%?
Can we? Yeah. Okay, yes. Okay, here we go. So it says here we are going to set up a Venn diagram to represent the situation that's going on. All right? So a Venn diagram usually starts with a rectangle. And it usually involves 2 things. Sometimes it can involve more than that. It gets really complicated. But it's going to involve 2 things. So here we go. We're going to draw 2 circles. 1, 2. And we'll call the first circle, we'll call this the girls. Okay? And then we'll call this side sports. Not boys, but sports. We don't know anything about the boys yet, in a way. That says sports. And you're right. You said 0.27, huh? Okay. So here's what we're going to do. Half of the girls play sports. There are 54% are girls, so half of them play sports. So we're going to put 0.27 on the inside of that. I wish I would have made that bigger. That means that out of the girls, 0.27 don't play sports. They're not going to be overlapped with the sports. Okay? This is the overlap in here. Right here is where girls and sports overlap. Do you see that? They overlap right there, so 0.27. Now, it says 62% play sports. So what should go in here now? No, because then that would mean 0.62 plus 0.27 is all of sports. The whole circle of sports needs to equal 62%. Yes, I already have 27% in there, so this would be 35%. Do you see that? So look at the circle for girls. The circle for girls has to equal 54%. Does it? Yes, 0.27 and 0.27. The circle for sports has to equal 62%. 0.27, 0.35. It's really nice to start with the middle and work your way out from there. Okay, and then how much total is all of that? 0.27, 0.27, 0.35. How much is all that? 89? 89? Does it end with a 9? Let's check. 0.27 plus 0.27, 89. Okay. 89. So 89 is inside those circles, total of 89. So on the outside of the circles will be 0.11 because the whole thing has to be 100% of the population of the school. Well, let's go ahead and answer their question. And these are tricky. These are hard. So letter A. It says here, what percentage of the students who play sports are boys? What percentage of the students that play sports are boys? Okay. Not what percentage of the whole place. Okay. What percentage of the students who play sports? So how many play sports? 62%, right? Okay. And of those, how many are boys? 0.35. You're either a boy or girl in this problem. I know that's not true nowadays, but in this problem it is. Okay. So 0.35. So the boys who play sports, okay, and that's going to equal 0.35 over 0.62, 56.45%. 56% of the boys play sports. Yeah?
You kind of lost me with the 0.35. Where did we get that from again?
Oh, okay. So if this entire red circle is sports, and 62% play sports, then these two in here have to equal the entire circle of sports, which is 62. That's why it's really good to start with this number first and then subtract out the other parts to get the parts away from that. That's the overlap of girls. So then when you have girls, and then when you separate that, now you have boys. So the percentage of boys that play sports would be 35 out of 62. Yeah. Okay, and then part C, or part B, we've already found the answer to this. It says, if a student's chosen at random, what's the probability that it is a boy who does not play sports? Probability that it's a boy that does not play sports. You actually have it in the Venn diagram. Do you know what it is? It's 11%. Yep. It's 11%. See, these are all the girls. I know you want to do girls and boys. You really do, but you don't. You can't here. But these are all the girls. Ooh. So then the boys that do not play sports are going to be outside of the sports and outside of the girls because they're the boys. So that would be 11%. Whew. That would be a lot harder to do without a Venn diagram. It really would. Okay. Now, the addition principle of probability says this. If you have the probability of A or B, right? We've done this already. We've talked about this. The probability of getting OO or AA, and we added them up, that's true. But in that case, there were no overlaps. You can't have type O and type A at the same time. Some things overlap sometimes. So the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Okay? So that right there is really important. The ones we've done so far haven't had any, they're called mutually exclusive. There hasn't been any intersection at all. But when there is an intersection, you have to subtract. Do you remember this from AP Stats? Yes, it's horrible, isn't it? Yeah, it gets real tricky. Okay. let me just give you a quick example of that so that you're not so confused. Like, if I ask you, for example, just a quick example, what's the probability of getting a queen or a heart? Can a queen be a heart? Yeah. So these are not exclusive. A queen and a king are exclusive. A queen can never be a king and a king can never be a queen. But a queen can be a heart and a heart can be a queen. So you would have to do this. The probability of queen plus the probability of a heart minus the probability of a heart queen or a queen heart. Yeah, that's what it means. Okay? So what's the probability of getting a queen? 4 out of 52. Perfect. What's the probability of getting a heart? Do you know how many hearts are in a deck? 13 out of 52. Well, guess what I just did? I added up the queen here, and then I added the queen again. Do you see that? So then we want to subtract out the probability of getting a queen that's a heart would be, oops, minus 1 out of 52. That would be your answer, okay? Now you can take it out earlier. You can be like, okay, queens, there's 4 of them, and then the rest of the hearts would be, you know, you can do it that way, but this is essentially what you're doing in your head. All right, let's do another Venn diagram one for these, okay? So here we go. Number 5. Probability statistics gets tricky, real tricky. All right, it says here, ooh, got cold in here. That same high school, Pascal High School, it says 68% of the students have cell phones. It's got to be way higher than that here, right? 77% have iPods. Should we change that to iPad? Okay. It says iPods in your book. Isn't that cute? Who owns an iPod? Do you ever use it? Yes. Do you use it?
All the time.
So cute. They're so out of date. Okay. iPod. And then it says that 62% have both. 62% are spoiled. Okay. What's the probability that a student has a cell phone or an iPod? And then what's the probability that a student has a cell phone or an iPod, but not both? What we're going to do is we're going to make up a Venn diagram again. Okay? You're going to love Venn diagrams, or not, but they're very helpful.
We can't use that thingy and just show that.
Yeah. I want to show you on the Venn diagram, though, how it works, too. No! All right, here's your circle. Here's your circle. I made them bigger this time. So here we go. Start with the middle. Start with the overlap. Okay, this right here, and label things too. This is your cell phone, and this is the iPad. Okay? And then the overlap is going to go in the middle, the kids who own both, which is 0.62. 0.62. Now, look, how many kids then own just a cell phone? 6%. 6%. 0.06. That's hard to see, right? But if you look at cell phone, the entire cell phone circle has to equal 68%. That's really gross. It's getting ugly up here. Okay. Now what about an iPad? How many kids have an iPad? 0.15. Very good. Because all the kids, 0.62 plus 0.15 has to be iPad owners. Now, let's go ahead and see what they're asking for again. We want the probability that a kid is going to have, what'd they say? Oh, what'd they say? A cell phone or an iPad. Okay? Cell phone or an iPad. Okay. So, we can do this. Now, there's actually a few ways, huh? Now that you have the Venn diagram, what's the probability of having just a cell phone? Yeah, 6%. What's the probability of having just an iPad? 15%. So the probability of having one or the other is 0.21. No, that's wrong though. Because you have to also include the people who have both. right? Yes. That's actually the answer to the second question. I was thinking that. Cell phone or an iPad, or both. So we would want to add the 0.62, so that would be 0.83. So 83% have either a cell phone or an iPad. They could have both, but 83% of them do. Yeah, you just add up all of these. Cell phone, iPad, 0.06, 0.62, 0.15. Now the second question, see, I was thinking second question. It's the probability of a cell phone or an iPad, but not both. Cell phone, iPad, but not both. Just one of either one. And that was going to be the answer that I came up with there. So 0.06 plus 0.15, so 21% have just either a cell phone or an iPad. 83% have a cell phone, iPad, or both. Phew, tough, huh? Okay, and then the last part, you're like, what? No more, please. Part C, we'll go quickly through this. Tree diagrams. Tree diagrams. Tree diagrams are very helpful, okay? I'm going to show you with this last problem here how helpful a tree diagram can be. So number 6, here we go. It's about cookies too. All right, we have 2 cookie jars sitting on the counter. 2 cookie jars. They're identical, okay? So you're not swayed either way. Ooh, this one's cuter. I'm going to choose a cookie out of there. That's just dumb. All right, 2 identical cookie jars on a counter. Jar A and jar B. Jar A contains 2 chocolate chip, 2 chocolate chip and 2 peanut butter cookies. I'll abbreviate. Jar B contains 1 chocolate chip cookie. Wow, that's it? I need to go to the store. All right, we select a cookie at random. What's the probability that it is a chocolate chip cookie? 1 cookie. And what is the probability that it's chocolate chip? Yes. What?
Are we choosing from a certain?
Either jar. 3/5. That's your answer. That is incorrect. It feels like it should be, right? Because if they were all in the same jar, that would be true. But you have a 50-50 chance of picking one of these, and then after that, there's a probability of its own. So that gets tricky, right? Yeah, I like your 3/5. That's true if they were in the same jar. Okay, so here's doing a tree diagram. Here we are. Thank you. You did have enough time. All right, let's say you pick jar A. You have a 1/2 chance, 0.5 chance of picking jar A. Here's jar B. You have a 1/2 chance of picking jar B. Now, from jar A, you can pick a chocolate chip, a peanut butter, or a peanut butter, right? Chocolate chip, peanut butter, peanut butter. And the chance of getting each of those is what percent? 25%. Perfect. 0.25 for all of them, right? 0.25, 0.25. This is called a tree diagram. Do you see the tree forming? The branches? Okay? Now this tree down here is a little boring because in jar B, you can only just pick a chocolate chip. And what is your chance of picking a chocolate chip in jar B? 100%, so 1. Okay, so now what we're going to do is we're going to add up all the possible ways to get a chocolate chip cookie. So let's go this way first. 0.5 times 0.25. Okay? 0.5 times 0.25, which is 0.125. Do it again with the next one. You choose A, you get the probability of getting a chocolate chip cookie is exactly the same thing. 0.5 times 0.25 is 0.125. All right, and then we can also, instead of choosing A, we can go to B and get that chocolate chip cookie by doing 0.5 times 1, which is 0.5. And so the probability total that I'm going to get a chocolate chip cookie is to take all of my probabilities up here and add them up. So I have 0.125 plus 0.125 plus 0.5. And that's equal to 0.75. So what is 3/5? That's 60%, right? You actually have a better chance. You have 75% chance of getting a chocolate chip cookie. Because if you choose B, you automatically win. If you choose A, you have, there's some options in there. Okay.